Let's talk a little bit about VSEPR theory, or valence shell electron pair repulsion theory. Now, this is just designed to be a brief introduction. It's not an in-depth discussion. So let's look at water. We have H2O, so we have two hydrogen atoms, one oxygen atom. In the center, we have the oxygen atom. We have two bonding pairs, one bonding pair for each hydrogen, and we have two lone pairs for the oxygen. Now, I've drawn this so that the two hydrogens are 180 degrees apart from one another, and the two lone pairs are at 90-degree angles to those bonds. So that would look something like this. Now, valence shell electron pair repulsion theory is looking at the repulsions between electrons. Now remember, the electrons are negatively charged, and so one set of electrons, one pair of electrons, will repel another pair of electrons, just like these balloons are pushing back against each other. Now, they're trying to get as far away from each other as they can while still being close to that oxygen nucleus in the center. Because remember, that oxygen, at the center of that oxygen atom is a nucleus. That nucleus has a positive charge, and so these negative charges in those electrons are attracted to the positive charge of the oxygen nucleus. They're also going to be attracted to the charges at the center of those hydrogen nuclei as well, and they'll be repelled by the other electrons around. So with this sort of structure, again, this is the sort of structure that I have here, where we have the two lone pairs and the two bonding pairs. Now, if I give that structure a little bit of energy by shaking it, it will rearrange into a three-dimensional structure. In this case now, we have gotten to a lower energy structure, which means that those electrons are farther apart from one another. Now, it's a little bit difficult to see with the balloons, so I'm going to pull out some molecular models. So we have a structure that looks something like this, where we have the oxygen atom in the center. We have these sticks that represent the electrons. They have sort of a three-dimensional shape that is roughly similar to what the shape of the orbitals that those electrons would be occupying. And then we have the two hydrogen atoms, these white balls on the ends of those, on two of them. The other two have nothing on the end, indicating that there is no atom at the end of that pair of electrons. Now note here that the angle here is not 90 degrees. That angle is a little bit bigger than 90 degrees. That angle in this case is 109.5 degrees. And so we've taken that angle from 90 degrees, like we had when it was confined to two-dimensional space, and by allowing it to expand into three dimensions, we now have allowed those electrons to get farther away from each other. Now this structure, if we have four atoms bonded to it, is called tetrahedral, because if we imagine a triangle shape on each of the sides here and the bottom, we have four sides to our three-dimensional shape, and so that's a tetrahedron. So this is a tetrahedral electronic geometry. And in this case, where we have four atoms bonded to the central atom, like we have in methane, this is then a tetrahedral molecular geometry. If the number of atoms bonded to that central atom is equal to the number of bonding pairs, in other words, there are no lone pairs, then the electronic geometry and the molecular geometry are identical. But if we say remove one bonding pair, so we turn that into a lone pair instead, remove one atom, now we only have three atoms bonded, and that fourth pair of electrons is a lone pair of electrons. Now I'm going to remove that to make this a little bit easier to see. We still have a tetrahedral electronic geometry, because that one is still really there. But with molecular geometry, we no longer have a tetrahedral shape. We now have a triangular shape, but it is not planar. These three atoms, the three white ones, are all in a plane. If I were to sit this on a table, those three would sit on the table, but the green one, the oxygen, that central atom, would sit above the table. And so this is not trigonal planar. This is trigonal pyramidal. It forms a pyramid. It's a very squished pyramid, but it's a pyramid shape. If I remove another atom, so we have two bonding pairs, like we have in the case of the water, we now have a structure that looks like this. Now we only have 3 atoms. Any 3 atoms must be coplanar, so it's got to be flat for the molecular geometry. And this structure is not linear, like I have drawn here. It is in fact bent. We again have that 109.5 degree angle there. And then if I remove that last atom, well, now we only have 2 atoms. 2 atoms, any 2 points must always be collinear. And so if we only have 1 atom bonded to the central atom, well, then it's always going to be a linear molecular geometry. Now we have a few different possibilities for the number of atoms around that central atom. We could have 2 regions of electron density, in which case we have an electronic geometry that is linear. Or we could have 3 regions of electron density around that central atom, in which case the electronic geometry we have is trigonal, planar, because again it's flat. We could have 4, like we saw with the tetrahedral geometry, this geometry. We could have 5. Now in this case, this is a different sort of structure. In all the previous ones, each of those positions for where the electrons were was identical. But in this case, we have 2 different positions. We have the axial positions, these 2 that are 180 degrees apart from one another. Those are the 2 tan-colored ones. And then we have the equatorial positions, these 3 gray ones. So if you imagine this as the Earth spinning around its axis, where the 2 poles are, the North Pole and the South Pole, those are the axial positions. And then where the 3 equatorial ones, where the equator would be, those are what we call the equatorial positions. And so those equatorial positions are 120 degrees apart from each other and 90 degrees apart from the axial positions. Those axial positions are again 90 degrees apart from the equatorial and 180 degrees apart from each other. So when you're building a molecule using 5 regions of electron density around that central atom, bear in mind that you have differences in those 2 different environments. When we have 5 regions of electron density, this structure is trigonal bipyramidal. The last structure we have is with 6 regions of electron density. Again, we've returned to all 6 positions are identical, and all 6 have 90-degree angles with respect to all of the other positions, with the exception of the one that's 180 degrees apart from it. This structure is called octahedral. Now let's talk a little bit about hybridization. In order to get these structures, we need to have atomic orbitals that have these positions relative to one another. The problem here is we don't have these in any atoms. The atomic orbitals are s orbitals or p orbitals or d orbitals or f orbitals, and none of them are 180 degrees apart from one another. So what we have to do is combine together 2 orbitals. In this case, we need 2 orbitals 180 degrees apart. We can combine together one s orbital, the only s orbital in the energy level that we're looking at, and one of the 3 p orbitals. We can mix those 2 orbitals together and generate 2 new sp hybrid orbitals. And those hybrid orbitals do have this geometry where they are 180 degrees apart. So if we need 2 orbitals, we'll mix one s and one p to get sp hybridization. If we mix one s with 2 p's, we get sp3 hybridization. If we mix all 3 of the p's, we get sp4 hybridization. If we start mixing in d orbitals, we can then get sp3d hybridization, where we have 5 orbitals, or sp3d2 hybridization, where we have 6 orbitals. Now in your notebook, you should have a row in there for each of the molecules or ions that is listed in the procedure. Each one you should have a row that looks something like this. You have the molecular formula and the Lewis structure. You should fill this out before you get to lab. Dimensional structure, you're going to leave this blank and we'll fill this in lab. You'll have the bonding pairs. You should again have this filled out, and the lone pairs, you should have this filled out. So I filled these out with 2. In this case, for the bonding pairs and the lone pairs, we only care about the bonding pairs or lone pairs around that central atom. So in this case, for the oxygen. If we had a lone pair of electrons on the hydrogen, we don't care. We're not going to include that in our count of lone pairs, because we're only interested in here in the number of electrons around that central atom, the number of regions of electrons around that central atom. Now, be careful, because if you have a double or triple bond, we would have a tendency to count those as 2 or 3 bonding pairs. But the double or triple bond, the second and the third in the double or triple bond, are in the same region in space, for purposes of this experiment at least, as that first bond. And so we're going to count single bonds, double bonds, and triple bonds all just as one bonding pair. The other boxes that you have, the electronic geometry, the molecular geometry, the hybridization, and the bond angle, you should leave blank. You'll fill those in during the lab experiment itself. Now, how do we represent a three-dimensional structure like we had with water in 2 dimensions? Well, first, my suggestion is to maximize the number of atoms that you have coplanar. So in the case of the water, let's see if we can get both hydrogens and the oxygen in the plane of the paper, or the plane of the whiteboard. So let's put one hydrogen over here, and let's put the oxygen in the center. And then that angle we said was 109.5 degrees, so that's going to have an angle that looks something like this. And now we need these 2 lone pairs of electrons on the oxygen. Now, thus far, everything that I've drawn has been in the plane of the board, in the plane of the paper. And so I can represent the bonds, or these electrons in the bonds, or the bonding pairs, as just plain sticks, like we would normally, like I did over here in the Lewis structure. But to now show something that's coming towards us, towards our eye, we're going to use sort of a perspective drawing. And imagine something, the closer end, the end that's closer to you, is going to appear wider, like with my marker. If I rotate the marker so that one end is closer to you, that end becomes wider than the other end does. And so that end, we're going to draw a sort of triangular wedge shape showing that the wider end of the wedge is closer to our eyes, and then I'm going to put a lone pair of electrons there. Now, it doesn't have to be a lone pair. We could have that wedge if we had another atom bonded there. And again, I'm going to do a similar sort of wedge, but in this case, to show the wedge going into the board away from our eyes, I'm going to use a dashed set of lines. And I'm going to draw that lone pair a little bit smaller as well. So I drew this lone pair wider on that. This end is wider than that end, showing that this lone pair is closer to our eyes, closer to our perspective, and this lone pair is sort of behind it and inside the board. So again, that three-dimensional structure you'll draw during lab itself.